Today we're looking at composition of functions, and that's this little symbol that you see right here. It's an open circle right in the middle. Now it's not multiplication, all right? So we're not multiplying them. What we're doing is we are going to take this function that's listed first with that letter f, and then we are going to plug into it another function. So this tells you what the input is. We're going to input that second function into the first. So this is the way we say it. We say f composed with g of x, because x is the common input. Or we can say the composition of f with g of x. We can also show it this way, right? Because in the parentheses, that tells you what the input is, and they both have the common input of x. So we would take this function and plug it in as the input into the first listed function. So let's take a look at that. So one aspect of this is just the algebra. How do you combine these in this way? There's another aspect, and that is identifying the domain. So let's first of all identify the specific domain of the individual functions before we then run the composition of them. So you might remember when we have a denominator with a variable in it, to identify the domain restriction, we take that denominator and say u cannot equal 0. If you have a polynomial, there's no restriction at all, so you can use all real numbers. There it is in interval notation. So if we run this composition, the composition of f with g of x, what we're saying is take the very first letter, that's the function we start off with, and then we're going to plug into it whatever we see on the second letter. So to help keep this information organized, I'm going to use my secondary color here so that you can kind of see what the input is. So the input is the x plus 3. Where does it go? It goes here, it goes here, right? So wherever you see the x, that's the symbol for input. So the function of f evaluated with the input of x plus 3 means we have 1 over x plus 3. And then you simplify if possible. That does not simplify. So that's the answer. Now you'll notice the denominator is different than the original, so we have to reconsider what the domain restriction is. So we're going to take that denominator and we'll say u cannot equal 0. So x cannot be negative 3. So this domain restriction of x cannot be negative 3. So this composition is only true as long as x is not negative 3. The reason why it changes like this is because we are allowed, when we're taking this input of x plus 3, we're substituting that in. We're bringing with it no domain restriction. We can plug in any number we want, even 0. So originally we could not plug in 0, but now as we're bringing in a new polynomial with a new domain, we're allowed to plug in 0. It's just that we can't plug in negative 3. So that changes on us. Here's another example, number 2. When we have a radical, you might remember to find that domain restriction, we take that expression out and set it greater than or equal to 0, and we isolate the variable. So putting that in interval notation, we're saying we're allowed to plug in negative 3 and values bigger than that, and we'll get a real answer out. Here on the second function, we do have a fraction, but the denominator is 2. You're allowed to divide by 2, that's fine. So x in the top doesn't really do anything. It's really, think of it like 1/2 x. So it's a type of polynomial. In other words, there's no restriction. So now let's run the composition. Identifying that first letter is f, so we start off with the function f of x equals square root of x plus 3. And then we're going to identify the input. The input will be this x over 2. It goes here, it goes here. And so when we evaluate the function with this new input of x over 2, we have square root of x over 2 with a plus 3. Now we could find a common denominator and combine those over a common fraction. That would be better. But we're really kind of focusing on the domain. That's like the bigger emphasis in these series of questions here. So notice that what is changed under the radical is different than what we started with. So that means our domain restriction is different as well. So this is not quite in simplified form, but we're getting it to a point where we can now evaluate the domain. So if we take a look at the domain, we're going to take that expression, set that greater than or equal to 0, and then we're going to work to isolate our variable. So we get x is greater than or equal to negative 6. So now we're able to plug in negative 6 and any value larger than that. So that's our domain. If we were to simplify this farther, we'd have to rationalize the denominator because we can't have a radical in the denominator like that. So just be aware this is not the final simplified form because we're really focusing on the domain here and how that changes. So with the next examples, we will be taking it all the way, simplifying it wherever possible. Here we have two polynomials, so that means the domain is all real numbers, so there's no restriction here. And what we're taking a look at is what if we change the order of the composition? Here, we're using the function f, and we're plugging into it the function called g. And this is the other way around, starting off with the function g and plugging in f. And the question is, will we get the same answer? So that's kind of a secondary question as we go through these examples. All right, so starting off, here's example 3, taking the function called f, which is the 3x squared plus 2. We will plug into that the function called g. So that's the 2x. Where does it go? It goes wherever you see that input symbol. And so we have f evaluated at 2x. So 3 times the input squared. Again, the input is 2x. And you still have that constant term of plus 2 on the end. So think of your order of operations, exponents before multiplication. So we have 2x times 2x gives us a 4x squared. Now we multiply, and we cannot combine any farther than that. That's our final answer. What's our domain? Our domain on this is going to be all real numbers because it is still a polynomial. Now let's do it the other way around. So now we're starting off with the function called g of x, which is the 2x. And then we're going to plug into it the function called f, which is my 3x squared plus 2. So that'll be dropped in here and here. So evaluating the function g with an input of 3x squared plus 2 means we have 2 times this input, 2 times this 3x squared plus 2. Distribute the 2, we have a 6x squared plus 4. So they're obviously different. They're not the same. So that's just something to notice. So our domain here is, again, all real numbers because we have a polynomial. And in number 5, this is a little bit of a twist on the problem. What if you take the function and plug into it itself? All right, so the same function is its own input. So we are looking at using f of x, which is the 3x squared plus 2. We're going to plug into that the same 3x squared plus 2. Where does it go? It goes here and it goes here. So evaluating the function with an input of 3x squared plus 2 means we have this multiplier of 3 out front. Here's my input squared with the plus 2 on the outside. Again, my input is that 3x squared plus 2. So we have a binomial that we have to square. So keep in mind we have to FOIL it out. So to make it a little bit easier to follow, I'm going to write out this binomial being multiplied to itself so we can go through that foiling process a little easier. Right, so that's the 3x squared plus 2 quantity squared. So that 3 will stay on the outside for a while. That plus 2 will stay on the outside for a little bit. Let's FOIL this out. So first times first means we have 9x to the 4th. And those outside terms gives us a positive 6x squared. Inside terms is another positive 6x squared. And the last of each pair is positive 4. So I'm going to do 2 steps. I'm going to combine those like terms in the middle. That'll be a 12x squared and distribute the 3 as well. So we have a 27x to the 4th plus 36x squared plus 12. And there's the plus 2 at the end. Finally, we can combine those constant terms. That'll give us a plus 14 at the end. So it's a polynomial. So again, you can see that our domain is all real numbers. So you can kind of see the system that we're using here. It's very sort of regular, and in a case like this, we're focusing on the algebra, as the domain was just all real numbers in each case. So we'll finish up with these last 2 examples, and here we're kind of coming back to the domain again as the point of emphasis. So we're going to simplify these problems completely, but also take a look at the domain to see how it might stay the same or change. Let's take a look at these 2. So again, we have a new set of functions here. If you take a look at the original function f, we do have a variable in the denominator that has a domain restriction, And if you work that out, x cannot be positive or negative 1. And in the second function, that domain, that's a polynomial, right? So there's no restriction here. So let's run the composition, starting off with the function called f. So we're going to plug into that the function called g, which is this binomial of x plus 1. So that'll go here and here. So f evaluated with an x plus 1. Plugging in that x plus 1 in the denominator. This is what the setup looks like. So we have to FOIL this binomial again. Be careful, that's not just x squared and 1 squared. It's x plus 1 times x plus 1. So we have a trinomial as a result. You have an x squared plus 2x plus 1. And then with the minus 1 at the end, those 1's will cancel out. So this turns out to be 3 over x squared plus 2x. That's the result of the composition. But notice the denominator is different, so we have to find this domain restriction as well. We take that denominator, x squared plus 2x, we say u cannot equal 0. Factor out the x. Separate each factor so it is not equal to 0. And we will get our two restrictions here, 0 and negative 2. So x cannot be 0 nor negative 2. And that's the final result. So we're finishing up with this last one, and this one is probably the most curious of them all. In each of the examples we've done so far, we've always had a situation where my input has come with a domain of all real numbers, no restriction at all. So this is where it's now different. My input is the function of g, which is root x. And because it's a radical, that means it automatically has an input. So here we are just kind of labeling it and bringing it to your attention. There is a domain restriction on this input. So what happens when you plug that in and you're already limiting the domain to begin with? All right, so here's my first function, f. F of x is the x squared over 2. We're going to plug in this. So it's not just the root x, it's the root x with the domain restriction. So that tags along. Again, that'll go here and here. So we have f evaluated at root x, but it has a domain restriction. And we normally don't put it here, we kind of put it at the end, so I'll put it here at the end. So here's my input squared over 2, and that input is my root x, but it still has that domain restriction of x has to be greater than or equal to 0. So that tags along for the ride. What that means is when I'm plugging in the root x, I'm not just plugging in a root x, I'm plugging in only the inputs that make a root x give me a real answer. So I can plug in a 0 and I can plug in a 1, but I cannot plug in a negative 1 or a negative 2, right? So that's why we have to consider this. And the reason why it matters so much is because when we simplify this, it looks like the square root disappears, right? It looks like the radical is gone. Does this mean I can now plug in anything I want? No, because we're only plugging in limited numbers because my input was a radical x. That means I only have certain outputs. I only have an output of like 0 and 1 and 2. That means I can only have a numerator of 0 and 1 and 2, each of them divided in this way. So that domain restriction still exists. It does not disappear. That's the final result. So if you're plugging in an expression that has no restriction, like you saw on number 6, then you just reanalyze the problem to see what new domain restriction there might be. But in a case like number 7, when you have your input that contains a restriction on the domain, then you have to consider that as being part of the final solution as well.